Hi, welcome to the next lecture in the NPTEL course on Haskell programming. In this lecture, we will continue our discussion on folds. Recall that fold R is a way of combining in elements of a list. In Haskell, fold R means fold from the right, and the definition was as follows: fold R takes two arguments, a function f and a value v. The function f is the combining function. V is the initial value, and you want to combine the elements of the list using the function f with v as the initial value. Right? Fold R of fv empty list is v. Fold R of fv x colon xs is f applied on x and the recursive result of applying fold R fv on xs. Okay, so this was the definition of fold R. And to give you an example, and this example is easier if you think of f, instead of writing it as f x y, if we write it as x backtick f within backticks and y, that looks like applying an operator. So then one can write this, one can trace a computation as follows: fold R fv x1 x2 x3 is nothing but x1 f when you write it in the operator form, you don't need to provide parenthesis for this. Fold R fv x2 x3, which is nothing but let me which is nothing but x1 f x2 f x3 but fold R fv empty list is empty list, so you will get x1 f fold R fv empty list is v, so you will get x1 f x2 f x3 f v. Okay, so this is the way computation proceeds with fold R. And just for you to remember, if xs itself is built by using colon and empty list, and you can think of fold R v of xs as replacing the empty list by v and the colon by f. And here are standard examples: sum is fold R plus 0, product is fold R times 1, and so on. And we looked at this example also. Fold R colon empty list is nothing but the identity function. Fold R of xl goes to l plus plus singleton x, with initial value being empty list, is nothing but reverse, but it's a reverse that takes order n square time. As another example, we saw that concat was just fold R of plus plus empty list. And finally, in the previous lecture, we saw that sometimes there is no natural value to assign to the empty list. For instance, finding the maximum of a list of numbers, then in such a case you would use fold R1. Fold R1 is a version of fold R where instead of using a special initial element, you use the last element of the list as the initial element. So fold R1 works only on undefined non-empty lists. It is undefined for empty lists. Fold R1 works only on non-empty lists. So fold R1 F singleton X is just X, fold R1 F X colon X's is F applied on X and fold R1 F X's. Okay. So this is the thing, and you can define things like maximum is fold R1 of the max function. Recall that the max function is of, for our purposes here, let us think of it as int arrow int arrow int. Okay, so that is the max function. Okay, so now in general there is something that we need to know about recursion. Sometimes we if I make a recursive call f on, let us just think of recursion on lists, f of x colon x's, I can first apply f recursively on x's and then combine the result of the recursive function with my initial value. Okay. So this is make the recursive call first, combine the result with the first element. Or I could do the following, I could, so this is best illustrated using the sum function. So sum of empty list is 0, sum of x colon x's is x plus sum of x's. You are making the recursive call first and then combining it with x. Whereas there is perhaps slightly less natural, but quite natural in many circumstances. There is another way of computing the same thing, which is to pass an accumulator around. Okay, so sum of any list is nothing but sum into an accumulator, and you will start with the accumulator 0. And what is sum into any accumulator? If I want to sum the empty list into the accumulator, I will just return the accumulator. If I want to sum x colon x's into the accumulator, that is nothing but modifying the accumulator first and then summing x's into that accumulator. So summing x's into the modified accumulator. So this pattern you can think of as modify an argument slash accumulator and then make a recursive call. Right, so these are two different patterns, and fold R corresponds to the first pattern where you first make the recursive call and then combine. Fold L corresponds to this pattern where you keep an accumulator or some such argument which you keep on modifying, and you first modify the accumulator and then make a recursive call. Okay, so notice that I use the phrases you first modify the accumulator and then make a recursive call. It so turns out that Haskell will not follow this particular order, but logically what I am saying is that you make a recursive call with a modified accumulator, or whether you make a recursive call whether you combine the result of a recursive call with your some element, okay, the first element. Okay, these are the two different patterns. So make a recursive call with the modified argument. That is one pattern. Or combine first element with recursive call. With result of recursive call. Okay, so that combine first element with result of recursive call is the natural sum that you would normally write. Sum of empty list is 0, sum of x colon x's is x plus sum of x's, whereas modify make recursive call with modified argument is this sum into version of sum. Okay, so this is just to motivate to you the definition of fold L. Fold L is the second pattern that we looked at, the sum into kind of pattern. So fold L also takes a function under initial value, but you will do this from the left. Okay, so fold L of FV empty list is V as usual. Fold L of FV x colon x's is, note what is happening. You do fold L of F with the modified initial value and x's. Okay, so you apply F on V, apply F on V and x. Take that to be your that is the modified initial value, and apply fold L with the modified initial value. Okay, and if you expand it out, you will actually see that you are using V at the leftmost and you are combining these operators, this operator F in a left associative manner. Okay, which is why it is called fold L, left associative. Fold R is more natural in Haskell because you have a list structure, and fold R FV on the list is just the same as replacing empty list by initial value and colon by F. But fold L is also quite natural in many circumstances, and it's a nice alternative to have. Here is a very nice example of fold L, string to number. Okay, so I have a string which consists of digits. So I might have something like 0. I might have the string 0, 1, 2, or 3, 5, 0, 9, let's say. So string to num of this should actually yield the integer 3509 for me. And how do I make it work, get it to work? I will start with an initial accumulator. So I will say, so let me write a naive this thing, string to num of string equals go, string to num equals go of 0. Let's say go is my sum into kind of function. Go any number accumulator empty string means there is nothing more to combine, so I will just return empty string. Go accumulator, and if my string is has a digit followed by more digits, then what I will do is I will do 10 times accumulator plus digit to int of d. That is my accumulator, that is my modified accumulator, and I will do go this of d's. Okay, so let me write it clearer. So let me actually go accumulator prime, let us say, of ds, where accumulator prime equals 10 times accumulator plus digit to int of d. Okay, that is the kind of thing that I would, right, and this is the most natural way to do it, because adding a digit to the rightmost of an existing number is easy, as we saw when we tried to reverse a number, whereas if you tried the fold R route, you would start at the endmost and you will try to add one digit after another to the leftmost of a given number, which is harder. So fold L is the more natural way to proceed when you want to do this particular function, and there are many functions where it is much more natural to do processing like this. Okay, here this was an example where you wanted to add a digit to the rightmost. There one can think of other examples where it is much more natural to do fold L than fold R. Okay, and finally, rather than doing a naive recursion like this, we use fold L, and we just whatever we did in the go function for the inductive case, we do that, we take that to be the function here. you have n and c. N is a natural number, n is an integer, c is a character, and which represents a digit. So you do 10 times n plus digit to int of c. Okay, that's the combining function that you use. The initial value of the accumulator you use is 0. Okay, so string to num is just this. Okay, and just to illustrate how it works, suppose fnc is 10 times n plus digit to int of c, then string to num is nothing but fold del f0, and string to num 234, let us say, is fold del f0 234, but then you will make a recursive call with the modified accumulator f0 digit 2, okay, and then apply it on 34, which is nothing but fold del of f of fold del f, and then you modified the accumulator further, f applied on f0 digit 2 applied on digit 3. So, this particular thing applied on the string 4, finally you will get this expression, okay, which if you use f in infix mode will be 0 okay. So, you will have that, but then f applied on 0 2, so it depends on what way you want to expand the thing in. Haskell will do it from outermost in. The outermost f it will first simplify, it will say 10 times f of this expression plus 4, then this inner f of 0 2 etc. is nothing but 10 times f0 2 plus 3, and f0 2 plus 3 is nothing but 10 times 0 plus the number 2 rather than the digit 2, and then this it will expand 10 times 0 plus 2 is 2, 10 times 2 plus 3 is 23, 10 times 23 plus 4 is 234. So, you will get this. Okay. So, this is how you can trace the computation of a fold del. Okay. Good. Yes. So, now let's look at one other aspect of folds. So, look at recall the definition of folder. Folder fv empty list is v, folder fv x colon xs is f applied on x and folder fv xs. Now, if you consider some list like x1 dot 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 xn, then this will first expand to f applied on x1 and folder fv of the tail, and this will expand to f applied on x2 and then folder fv of its tail, and so on. Finally, you will get something like this. The point is, Haskell will not simplify any of these expressions till it has come all the way down to this form. Okay. So, for instance, suppose instead of f we used plus and instead of v we used 0, then you will have this folder plus 0 1 dot dot 100 will expand all the way down to an expression like this, and then it will simplify starting from innermost. Okay. So, this is what Haskell will do. Yeah, that's right. So, the point is that it requires a lot of space to internally, it requires a lot of space to carry around this huge expression. Okay. So, if you run this on GHCI with some flags turned on to tell you how much memory is being used, you will see that it uses quite a lot of memory. Okay. So, that is one thing. Another aspect of folder is that as we saw with the length function, the length function used a function f which required only one of its arguments, but that was the second argument. But sometimes you might have a situation where you use only the first argument, in which case, yeah, okay. So, we will come to that later. If f needs both inputs, it will be applied only at the end. Okay. So, what happens is that you need space to carry around a huge expression like this. Okay, let us look at the case of fold del. Fold del also suffers from the same problem. fold del fv x1 dot 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 xn is fold del f of fv x1 applied on x2, x3 dot 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 xn, but this thing is not simplified right away, not simplified right away. And then this thing is fold del of f and then yet another modified accumulator, but the accumulator is not actually modified by being evaluated, it is just a new expression. So Haskell will keep carrying huge expressions like this around, it will carry a huge expression like this around and then only it will start simplifying. And this is a result of what is called lazy evaluation used by Haskell. Lazy evaluation means that do some work only if it is needed. Okay, so I don't need, I can apply the definition of fold f without simplifying this expression. I can just keep it as fvx1 and apply the definition of fold del. So I will just go ahead and apply. Okay, only if I am forced to evaluate something in order to be able to compute some result, only then I will compute it. Otherwise, I will not evaluate a particular expression. I will keep it around. In the here, even in the case of fold R, for instance, there is no need to so to evaluate plus, I need to evaluate both arguments, which is why you keep on evaluating that. Okay, so only when you are forced to evaluate something, you will evaluate it. To evaluate plus on two things, you need to simplify both arguments to a number, which is why you are continuously computing like this. Okay, so fold del also suffers from the same problem. So if I do fold del plus 0 1 dot dot 100, I will have fold del plus some expression like this 2 dot dot 100, then some other expression like this 3 dot dot 100 and so on. Finally, I will have fold del plus of some huge expression like this applied on the empty list, which will return that expression. Now, at this point it will to evaluate, so I need to evaluate this expression to print the final result, let us say. Now it will start simplifying it from the innermost. Okay, so this is what is happening. So same problem as with fold R. So you need space to carry huge expressions around. So there is actually since we are talking about folds, one needs to talk about an important variant of fold del, which is called fold del prime. Okay, notice the prime here, fold del prime. And this is not automatically defined in the standard prelude, but you can say import wherever in your code at the very top line, you can say import data.list and within parentheses you can say fold del prime. That will import this and you can use it. What is the difference between fold del and fold del prime? Okay, fold del prime is what is called an eager version as opposed to lazy. What it does is it simplifies the argument immediately as soon as it gets it, and you might not be able to understand this code right now, it's a little hard, but just the point is that it uses some special function called seek, which stands for sequencing. What it does is it evaluates y. So yeah, so let's look at sequencing. Sequence seq is of type A arrow B arrow B. So it takes two arguments. The final value it returns is the second argument, but both arguments could be some expressions. The thing is that it evaluates the first argument first and then it evaluates the second argument. In case the second argument is an expression that uses the first argument, then it uses the simplified value. Notice here that seq has two arguments, one is fvx and the other is fold del prime fyxs, where y is just fvx. So it first evaluates y, it simplifies it to some expression and then it uses that in the second argument which it evaluates. Okay, so evaluate the first argument and then just go ahead and evaluate the second argument. In case the second argument uses the first argument inside it, then you will use the simplified value. Okay, that is the point of seek. All you need to know is that instead of fold L, it would be better to use fold L prime. Okay, so and the reason is this. Okay, so any function f has a eager version. So remember that fe is nothing but f dollar $e, because dollar is the apply function, but you can have an eager apply which is f dollar bang e. What this will do is it will evaluate e and then it will apply f on e. Okay. Okay, so now what is the result of using fold L prime? Fold L prime of y f y y naught x1 dot 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 xn will actually give you fold L prime of f y1 x2 dot 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 xn, where y1 is the result of applying f1 y naught and x1. It's the actual evaluated result, which is nothing but fold L prime of f y2 x3 dot 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 xn, where y2 is f applied on y1 and x2. So the result evaluated. So you won't carry, these are not expressions but results. Okay, so that is the difference between fold L and fold L prime. So yeah, so this is a variant of fold L that's useful to remember. So fold L prime of plus 0 applied on 1 dot dot 100 will actually be fold L prime of plus 1 2 dot dot 100 instead of an expression plus 0 1, and now this will be fold L prime of plus 3 3 dot dot 100. This will be fold L prime of plus 6 4 dot dot 100, and so on and so forth. Okay, then it will be fold L prime of plus 10 5 dot dot 100, and it will go on like that. Now there are two other useful variants of not variants but closely related functions to fold R and fold L, called scan R and scan L. Okay, see that fold R is of fold R produces a value, scan R will produce a list of all the partial values. Okay, so scan R is of type type A arrow B arrow B, just like fold R. Arrow list A, arrow there is an initial value missing, arrow B arrow, here also there should be an, okay, arrow B, arrow list A, arrow list B. Okay, so scan R FV empty list is the singleton list containing V, because V is the value corresponding to the empty list. Now for every suffix you will look at the value corresponding to that and then have it as part of the list. So scan R FV x colon xs is nothing but fx y colon ys, where ys is the result of applying scan R on FV xs. Okay, and notice here we use this at pattern. This is a way to refer to the same thing in two different manners. I want to refer to a list ys, but I also want to name the first element of that list. So I will say ys at y colon underscore, because I do not care about the tail of that list. So I am able to refer to y here, I am able to refer to ys itself here. Okay, so that is the point. Yeah, so scan R FV x colon xs is nothing but fx y colon ys okay, this is the important thing. So for instance, if I did scan R then I will get the list, this is a list of length 6 0 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 but when I do scanr, I will always get a list of length 1 more, because corresponding to the empty list I will have a value 0, that will be at the end, and then it will be the last suffix, which is 5, and then it will be the value corresponding to the suffix 4, 5, which will be 9, and then the value corresponding to the suffix 3, 4, 5, which should be 12, then 2, 3, 4, 5, which should be 14, 1, 2, 3, 4, 5, which should be 15, and 0, 1, 2, 3, 4, 5, which should be 15. So, this is the result I will get if I apply scanr plus 0, 0 dot dot 5. There is a scanl also, as you can imagine, and let us just intuitively try to figure out what all values would result. This will go with scanr will list all the values corresponding to the suffixes, scanl will list all the values corresponding to the prefixes. So, 0 is the value corresponding to the empty prefix, 0 is the value corresponding to the prefix consisting of only 0, and then 1, then you have the element 2, if you add all that it will be 3, then you have the element 3, if you add all that it will be 6, then you have 4, if you add it will become 10, and then 15. Okay. So, scanl is usually the more natural thing you want, because when you want partial sums you will try to compute it from the left, but sometimes it might be useful to do some all the partial sums for all the suffixes as well. Yeah, so and the definition of scanl is scanl here also the there is one argument missing, which I will correct in the files when I program actually. So, scanl fv empty list is the singleton list v, scanl fv x colon xs is y followed by scanl fyxs, okay, where y is fvx, okay, because you fvx is the result so every new accumulator you are going to list. So, every time you change the accumulator you will list that, okay, and finally corresponding to the empty list you are going to return the final value of the accumulator, which is also the overall value of the scanl, okay. So, this concludes most of the important bits regarding folds and scans, okay, regarding foldr and foldl. Finally, we will just do some an exercise just to illustrate the power of folds, but also to see how Haskell lends itself to easy reasoning about programs, just equational reasoning about programs, just like you would reason about algebraic identities, let us say, okay. Suppose I call a new function step xga. Step xga is g applied on fax, let us say, where now this is for a fixed f is fixed by the context, f is fixed by the surrounding context, not an argument of step, okay. Step takes 3 arguments xga and it applies g of fax, okay. So, that is the definition. Now, one can actually do proofs just like mathematical proofs by induction using Haskell. So, I claim that foldr of step g foldr of step g xs e is nothing but g applied on foldl fvxs. This is what I claim, okay. Okay, let us prove this claim by induction on length xs. Foldr of step g empty list e, remember foldr definition, foldr step g empty list should just give me g, okay. So, the point is in this foldr step is the combining function and g is the initial value, and the initial value itself is a function. And the combining function takes a function and returns a new function. This is just to illustrate the power of higher order functions in Haskell. So, folder, if you just look at this expression, folder step G empty list, that should just be G, okay, just by going by the equation of folder, because folder f v empty list is V, similarly folder step G empty list is G, okay. This is G, but E is nothing but foldel fe empty list, so this is nothing but G applied on foldel fe empty list, okay. So, this equation here is true when XS is empty list. Let us look at the inductive case. Folder step G x colon XS applied on E, but forget the last E. Look, just look at this. If you go by the equation of folder, it is just step applied on X and folder step G XS, and then this whole thing applied on E, okay. But yeah, here is where you use the definition of step. Remember step, let us just use some different names. Step YHB is nothing but H applied on FYB, okay. So, therefore, step of X folder step G XS E. So, here this H is playing, this whole expression is playing the role of H, this B is this E and this Y is this X, okay. Then I should get H applied on FBY, so I will get folder step GX applied on F E X, okay. FBY is nothing but F of E of X, okay. So, that is this expression here, folder of step G XS FEX, okay. Now, at this point I apply the induction hypothesis, because I am saying induction is on length of XS, I have X colon XS, XS is a smaller length, so folder step G XS anything is G applied on fold L of F that thing XS, but that thing here is FEX, so this is G applied on fold L F FEX XS, okay. And but fold L of F FEX XS is nothing but fold L of FE X colon XS, okay. See, so you just followed the definitions and argued just like you would argue about some trigonometric identities or whatever, and you are able to actually prove this thing by induction, okay, that fold L therefore can be expressed using folder. Finally, fold L therefore fold L FEXS therefore is nothing but folder of step function applied on identity function XS E, okay. This is how you define fold L using fold R. You can also define fold R using fold L and argue similarly by induction. I will skip this proof. Finally, here are some useful functions. Flip is a very useful function to have. So, recall that we suppose, so look at the colon function. This will take A arrow list A and then it will arrow list A, that is its type. So, if I give XL to the colon operator, I will get X colon L. Now, suppose I want to do, suppose for some reason I provide the arguments in the wrong order. I have the arguments in the wrong order, let us say, and I still want to apply colon to X and L. I cannot apply colon to LX because this is of type A and that is of type list A. So, what I want is, I want a function of type list A arrow list A, okay, and it is, and the function that is of this type is called flip colon, okay. So, for any function f, if f is of type A arrow, B arrow, C, flip f is of type B arrow, A arrow, C. What is happening is that once you're not flipping the function, rather you're creating a new function that takes the arguments in the opposite order. That's basically all that is happening. So you have an input function which is of type A arrow, B arrow, C, but once you flip it, you are allowed to accept the arguments in the wrong order and then produce and apply the function really. And for instance, here is a very useful this thing, yeah, flip colon list 1 dot dot 10, 0 is just 0 dot dot 10, okay. Normally you would say colon 0 1 dot dot 10, that gives rise to 0 dot dot 10, but flip colon 1 dot dot 10 0 will give you 0 dot dot 10. Why do I mention flip here? Because here is the point, fold R FVL can be changed to fold L flip F V reverse L, okay, because recall that what is fold R doing? Fold R is doing x1 f x, suppose I have a list x1 dot dot xn. Fold R is doing x1 f, let me use O plus as the notation. So I will have x1 O plus x2 okay, this is the result of fold R. Fold L will produce V applied on x1 and then that applied on x2, that applied on x3, finally applied on xn. Right, this is what the fold L will do. Now you can actually see that if I instead apply this fold L on the reverse of the original list, then I will have V applied on xn, then that result applied on xn minus 1, then finally all the way till you get to x2, and then, and you can see that if you sort of take this expression and reverse it, you will get this expression, right. So that is really what we mean when we say that fold R FVL can be changed to fold L flip F V reverse of L, okay. So that is another way in which you can relate fold R and fold L. Okay, here are a few more useful functions. Const is a useful function. Sometimes you might want to use, since we mentioned flip, we are mentioning other useful functions. Const is a very useful pattern to have. For instance, we had this length function. Right, so here this inner function takes two arguments and it ignores the first argument and does something to the second argument. So you can express that by saying const of plus 1. Right, so recall that functions of two arguments are really functions of one argument which returns a function which operates on the second argument. So const of plus 1 operating on x and y will just be plus 1 operating on y, which will just be y plus 1. Okay, so rather than writing this lambda expression, I could have just written const plus 1, and const xy is nothing but x. Yeah, that is right. Const xy is nothing but x. So recall that const plus 1 x y is nothing but const plus 1 applied on x and then applied on y. So, this const plus 1 x just becomes plus 1 and that is being applied on y, and that gives you a plus 1. Okay, so, const is a useful function. Dollar we already saw, dollar bang is the eager version of dollar, and yeah, here are some, I have just mentioned some simple ways of relating foldar and foldl, but this is really just for academic curiosity. You do not require to understand all this to be able to use foldar and foldl. This was just to tell you that you can also indulge in such exercises in Haskell, but I hope you found it interesting. Okay, so I will stop with this. We will next look at a demo session where we consider, where we just run some of these functions and see how they operate, and with that we will end our discussion on folds. Thank you.